Mona. So it is my pleasure to be here today for this keynote on declarative programming and education by Professor Shriram Krishnamurthi. He is professor at Brown University and vice president for programming languages at Brown. As you already know, he has an impressive curriculum with contributions in different areas, from software systems, from JavaScript tools, till his recent current work on Parrot. He has been working in different important areas for the last, I would say, at least 25 years on computing outreach, and co-authored many books. And in the last, I think, 5 or 6 years, he has been focusing more on computing education research. And this is actually very related on to what he will talk about today. So I'll stop here just to leave the floor immediately to Shriram for his talk.
Thank you. Thank you, Antonio. Grazie. It's very, very kind of you. I hope I can live up to all of that. So thank you, everybody. I know this sort of hybrid form is going to be a little difficult for everyone. We'll do our best to make it work. People, if there's something not working, I may not see things on the screen, so just feel free to yell out. Audio is always going to work, and we'll make this all work out. So thank you all for coming. I want to start by doing a quick recap of where introductory computer science has been for a while now. So let's look at where data structure progress has been since the 1970s, right? So people of a certain age will recall that in the 70s, we taught everything in Pascal using arrays, and then the world moved on. We moved on to C, and then we moved on to C++. And then, finally we got over to Java, and finally we moved from arrays to maybe array lists. And, now we're in a great new world, and everything is now done in Python, and we have moved from array lists to associative arrays. Okay. This is a sort of depressing story about mainstream computer science education and how little progress we have actually made. And there's this sort of giant blob of what is typically called CS1, sort of introductory programming, which is this sort of boring old thing, right? It's like even people who went to college in the 70s and 80s can look at a modern introductory computer science course, and you would be surprised by how little has changed, right? We're still like banging away at variables with for loops and, old metal workers or something like that. It feels like really not much progress has happened. That's the sort of sad story. Okay. But this educational world is actually under a lot of pressure, even if the people teaching this stuff don't entirely realize it. Right? There's what I would call sort of pressure from above, which one might call the sort of unreasonable effectiveness of data, right? Like what has happened in computer science, for better and worse, through the introduction of massive amounts of data. There's what I would also call pressure from below, which is there are now all kinds of systems and all kinds of ways of getting working software that don't seem to require any of the things that we teach in introductory computer science. There's a lot of conversation we can have about this. Some of you who are on social media know this has been a sort of obsession of mine. But I think it's important because we need to have a conversation about what it is we're trying to teach and what it is that people want to do and what we can do without conventional teaching. I think these are important questions. But another very important sort of pressure from below is the act of synthesis. And of course, when I say synthesis to this audience, everyone thinks of formal synthesis. But I think at least as exciting, if not more exciting, is the idea of, code synthesis from text. So for example, GitHub Copilot and systems like that are doing some pretty bizarre things, but also pretty amazing things. And it's worthwhile for us to rethink what computing education means in a world where this is true. Right? I think we're very close to the point where we're going to end up recapitulating all the debates that happened in math education once calculators came about, right? What do you really need to know? How much can be done by the calculator and so on? Those same debates are going to become relevant for us. And then there are many other pressures also whacking away at this thing. There are all sorts of other disciplinary needs. There are very real diversity concerns, very serious societal impact concerns, and so on. Okay? And so this nice, beautiful, like all-encompassing, dominant CS1 is actually being chipped away and whacked away and cracked away and broken away by all sorts of forces. As I said, even if the people teaching this stuff don't entirely realize it. Okay. Now, let me let you in on the biggest secret. Okay. While these folks are still doing their old like metal banging, for loop curricula, the biggest secret is we've already won. If you look at the places where, for example, data science programming is headed, right? There are people like this is from Hadley Wickham's book. You don't have to read any of this text, but basically it says, look, basically we should have been programming functionally all along, and I'm going to teach you how to do that, right? This is not like a functional programming person coming and telling the world how things should be done. This is an actual living, breathing data scientist telling the data scientists, talking to each other within their community, saying there are all these ideas from the outside that we should be bringing in. If you look at a bunch of modern frameworks, React and jQuery and so on, what you realize is that these are actually sort of very declarative frameworks. Not all of them and not completely, but they're headed very much in that direction. So what's interesting is you might think that people are programming in Python or JavaScript or something like that, but what they're actually doing is programming in these frameworks. And what the frameworks are actually doing is moving their programming to a very different place and one that we might recognize. So, just as an example, a few years ago, we took jQuery as a case study and went and studied the structure of jQuery. Right. And it turns out that jQuery can actually have imposed on it a very rich, very dependent type structure of the sort that we would immediately recognize. And that's kind of what's going on under the lid in jQuery. And we can explicate this and build these type systems out and have people program with them. So the point being that these programmers are already headed where we want them to head. Okay. If I'm being facetious, there's kind of like a Greenspun's 10th rule going on, right? Sort of any sufficiently complicated modern framework is basically, headed to being a declarative language. I don't know how many of these adjectives apply, and they apply in different to different degrees to different frameworks. But this is my claim, right? The big secret is we've already won, and that's the end of my talk. Thank you. If you have any questions, Okay, no, that's not quite the end of my talk. Sorry, hold on. That's the good news, okay? That's the good news in terms of where programming is headed. But what I want to talk about is the bad news. Because remember, this talk is not about mainstream programming. This talk is about computing education. And in computing education, there's still a whole lot more we need to be doing. So let me give you a kind of a cartoon sketch of how sort of student programmers, how the lives of student programmers works. Okay, so I'm going to draw you this sort of very scientific graph. And on one axis, I'm going to have lines of code. And on the other axis, I'm going to have the student's current mind state, the level of frustration that they feel. Okay. And what happens is, and now this is a phenomenon that the people listening to this talk will not relate to well, partly because you're the survivors, you're the ones who maybe didn't feel this, so of course you don't realize that that's what your students feel. But when you initially hand out a problem, there's this like problem statement or some difficult thing to do, and a big blank, IDE editor staring at them, and somehow they have to fill up this editor with these magical incantations that will exactly solve that problem, right? So what happens is they start off in a very frustrated, worried state, and then as they start to make progress, things get better and better, and things go, So this is blank page syndrome initially, and then they start to make progress, and things get better, and things get better. And then at some point, they're kind of halfway there. They sort of have a solution, and it's not quite working. It works half the time, but doesn't work the other half the time. And I like to say that students are like 3D printers. They work by additive manufacturing, right? When something doesn't work, it's like, well, how did I get here? By writing lots of code. So the solution must surely be adding more code, right? So they start adding more and more code, and eventually, like, everything goes haywire. And they walk into your office and they say, my program doesn't work, right? And we could have a whole talk about this phenomenon and what to do about it. That's not really what I want to focus on today. But what I want to say is, I think we should recognize that this is sort of the life cycle of how the student experience goes, and this has all sorts of consequences, diversity consequences, and so on. And what we should be doing instead is trying to figure out how to turn this graph into a graph that looks maybe a little bit like this. Okay. And there's actually a whole lot in the education world that is relevant to this. There are lots of theories and tools and techniques and so on, and they have fancy names. And since this is not meant to be an education tutorial, I'm not going to tell you what these words mean. Some of them will make sense to you sort of intuitively, some of them will not. But what I want to say is we can use a lot of these ideas to improve the student experience. Okay. So, what I want to do now in the next part of this talk is I want to give you two case studies of experiences of students and what we can do to relieve those experiences and make them better. All right. So, before I do that, I'm going to stop for a moment and see if anybody has. I don't see. I see something in Q&A. Let me just take a quick look. Um, I wonder if the claims that people in these. So Andy's going back to my question from a few slides ago. I wonder if claims that people programming in these frameworks are doing FP is measurable in some way. Yeah, I think that's a very good question, Andy. I suspect that we can find a fair bit from this is the kind of thing that corpus extraction would help with. I'm actually reminded of a seminal paper from the 1970s. So Rich and Waters were building, Chuck Rich and Richard Waters, I believe, were building this thing called the Programmer's Apprentice. And Rich actually did, Waters, maybe both of them, did this great study where they looked at Fortran programs that were actually written in a for loop style, but were trying to extract higher level features out of the for loop style and pointed out that there's actually sort of a much richer semantics to these for loops than what is being written. Right. And this was their motivation for thinking in terms of stream processing and so on. So I think these kinds of corpus studies actually go back to the 70s, and it certainly makes sense to do that now. So I hope that answers your question. I think that is a very interesting question for somebody to ask and answer. Okay. All right. So let me now give you two concrete examples, sort of case studies of problems students face and things we could do about it. So I'll start with something that's a sort of very introductory point, which is let's help students understand problems before they program. Now, you might wonder what's the issue here? Well, the issue is it turns out there's a fair bit of evidence that students often solve the wrong problem. Okay. Now, this is a little different from solving the right problem incorrectly. You can solve the right problem incorrectly, but they solve the wrong problem entirely, which if you don't look at it the right way, if you don't have the right evidence, you might think they solved the right problem incorrectly, but they've actually solved a different problem entirely. Why might this be? Well, maybe they misunderstood the problem statement. They didn't read it carefully enough. But there are actually subtler reasons why this happens. So students, for example, when given a problem, will often recall schemas that they have in their head. They'll recall things that they know. And that recall process can lead them to a different place. So, for instance, you might have lectured on something the previous week, and they might recall what you said in class, and they might say, their brain effectively thinks either implicitly or explicitly, I bet they're testing me on this thing that I did in class last week, and they go off and solve that, and you have subtly given a different problem, and that's not what they solve. Okay. So what can we do about this? Well, of course, we grade them and give them some feedback after the homework's done, but that's too late, right? I mean, first of all, they've already forgotten what they're doing. They're moving on to another homework. And anyway, the reason you put that problem in there was probably some learning objective, and that's now been lost. Okay. So when I talk to people will often say things like, oh no, we use an auto grader. The problem is auto graders come too late. First of all, you have to have enough of a solution that you can give to the auto grader so that it can give you feedback. And by that time, you've already sort of finished the work, right? The other problem is there's this sort of fear of change. Students are extremely averse to throwing out code and starting all over again. So if they've gotten on the wrong track and they're never going to get to a solution from where they are, they will still, as I said, the 3D printing thing, right? They'll keep trying to solve it rather than retrenching, starting all over again. Okay. And I want to say more generally, as a community that thinks about programming and languages, we spend an awful lot of time understanding, focusing on understanding programs. We don't focus enough on whether students understand problems, right? So that's the question I'm really getting at. Now, of course, there's a tradition, in mathematics and so on, where we'll often say, state the problem in your own words. Now, this is a very noble idea. It's a great idea. The problem is beginning students don't have their own words. If they did, they probably wouldn't be in our classes, right? And some of you may have had this experience when you ask a student to do this. They'll basically restate the problem statement, but replace the words, several words with like synonyms, right? That's not actually showing their understanding. That's just solving the syntactic task. All right. So what can we do about this? Well, let me do the following. Here's what I'm going to do. So I want everybody to switch over to the chat window, and I'm going to give you a little task. We're going to do a little homework exercise now, right? Or it's classwork, I guess. So what I would like you to do is I would like you to provide examples, that is input-output pairs for a median function. Okay, so function median that consumes maybe a list of numbers, and it's going to produce the median. Go for it. I'm going to look at chat now, and I want to see everybody typing. Okay, stop reading email. Go. People in the room, I don't know if you can chat or maybe you want to just call out something. Okay, great. Andy's given me a great one to start us off. Thank you, Andy. 123 gives us 2. Torsten, very good. Excellent. Other examples. I want to see at least 3 or 4 more before I go anywhere. Stephanie, excellent. Great. Up. Good. I'll wait for 2 more before I move on. Ah, very good. And let's see, 1, 3, 2. Ooh, very nice. Okay. Okay, good. All right, well done, Alan. Okay, so you've hit most of the things I wanted to hit. So let me first point out something that we've just done, right? I asked you to state the problem in your own words. That's what you've just done, okay? But you've done it in a very concrete way, right? So you've given me concrete examples in your words of trying to interpret the problem. And there are actually some interesting interpretations. So Alan, for example, has asked us what happens in the case of the empty list. Torsten and maybe Stephanie and maybe some others also have asked us, like, let's try to clarify what happens if there's an even number of elements, right? What are the boundary conditions? Now, of course, once you've written these, you can also use these as test cases later on. If you're a student who struggles to come up with even these examples, there's a really good question to ask about whether you should be writing any code at all, right? If you have this little understanding of the problem, maybe that's the thing that our education should be focused on addressing, through help sessions or whatever, rather than looking at code, okay? But the problem is, if you just write inert examples, like you've just pasted a bunch of things into chat, right? And, they're kind of useless. Like they just sit there and then they might be wrong. And there's actually evidence, Kathy Fizzler and her student, Francisco Castro, found that students won't even write them if it's completely inert. They're just like, yeah, I'm told, I know it's a good thing, but I'm not going to do it because what's the payoff? Okay. So here's a really simple idea, right? What we're going to do instead is we're going to take the examples that the students wrote and run them against known correct and known buggy implementations. And the beauty of this is we can do this right now. I can take all the things you wrote in chat. You haven't written an implementation. You may not even know how to implement median, but I can still give you feedback about the quality of your examples, right? I give you feedback about how well you're doing. So you might say, oh, this sounds like mutation testing, and it sort of is, but there's a really big difference. Because in mutation testing, you're going to generate as many mutants as possible. You have to deal with the sort of oracle problem. But the key there is to figure out, is the test suite of good quality or not? Here, what I'm more interested in is, are you actually, do you have any misconceptions? And if so, can I ward them off early on? Okay. So there's a system, there's this IDE called Exemplar that we built on top of Pirate, which is this programming language we're building. And so here is Andy's example, right? So if you write median of list 1, 2, 3, Exemplar will come back and tell you 2 things. It'll tell you it's valid, and it also tells you you've actually caught one of the buggy implementations, okay? Now, one interesting thing about this example is you have not yet demonstrated to me that you understand the difference between median and average. So here's an example that actually, and some of you in chat had, interesting examples that tried to get to that distinction. And so now if you do this, where clearly now you're distinguishing between median and average, now it catches another buggy implementation. So now, as you might guess, the 4th buggy implementation is actually average. And so when we run the first example, you still haven't ruled out average. Now you've ruled out average. Okay. Another example, I think Torsten and Stephanie had an example along these lines, which is, what is the median? It turns out that even at the collegiate level, many students think, well, they've been told the median is the middle element. And textbooks never tell you it's the middle of the sorted list of elements. And so people actually think that the median of 132 is 3. I have about 30% of my class is not completely sure and thinks it may be the case, right? And so if you do this with Exemplar, Exemplar will tell you, I'm sorry, this is incorrect, so I can't even tell you about the other things. right? So this isn't giving the student the correct answer. That's on purpose because we don't want people to just like write junk, junk tests and get all the answers. But this is now a point where if the student has this misconception, they can go and talk to the core staff and say, help me understand this before they go off and implement something and then find out that they've gotten themselves into a mess. Okay. So there's a bunch of research we've done on this, studying this question. One of the interesting things is the third paper in this list is entitled, Will Students Write Tests Early Without Coercion? So it turns out the exemplar implementation has both some nudgy behavior and some gamification in there that generally make sure that students will in fact do this voluntarily, which means that problem understanding goes up significantly. And we see huge improvements to the problem solving they do. So it turns out it's not that they couldn't program, it's that they were just solving the wrong problem. Okay. And just for full, sort of to be proper scientists about this, the last of these papers is actually a qualitative analysis. We basically present exemplar to students as like a TA that's already there who can answer questions at all hours of day and night about the definition of the problem. So then we did a qualitative analysis to find all the ways in which it doesn't suffice. And so that's sort of, things that can trigger future work. Okay, so that's one example. Let me give you another example. So this was like sort of helping beginning students with beginning programming. Now I want to switch to a very different topic, which is teaching people how to write formal properties. Okay, so I'll just take a quick look at chat, and I don't see any questions here, so I'll assume that everyone's okay for now. All right, so we're moving into an era where verification tools are finally a real thing. Synthesis tools are a real thing. And as I said, we're moving the abstraction of programming higher and higher, which means pretty soon we're going to have to think very hard about the pedagogy of writing formal properties. And unfortunately, the computing education research community doesn't think about these kinds of questions at all. So this is the kind of question that I've been interested in for a little while now. And my perspective here is that, if you think about, and I'm going to give you a new pseudo-scientific graph, sort of between ease and power, and full formal specifications are sort of sitting at the top right? Like formal properties are very powerful, but they're not that easy to write, okay? Now, I don't know how each of you gets to that point with your students, but I'm very excited about the fact that there is a kind of formal specification there actually they can be quite good at, and particularly picking up on what I just talked about a moment ago, which is unit tests. Because unit tests are also a formal statement about what you're expecting. They're not a statement about a particular implementation. They're specifications. They're very easy to write because each unit test is independent of the others, and they're very weak, okay? So we somehow have to get students from doing this, which I just showed you we can have techniques for doing well, all the way to that. And I've been finding over the years that anytime I find like these big leaps, I'm really excited about trying to find some sort of, roughly midpoint between these things so that we can break this progression down. You remember my graph about trying to take the mountain and turn it into a series of hills or little bumps? This is one of those examples, okay? And so the particular technique we've been using is property-based testing. And we've been doing this both in our introductory course and in the formal methods course, where we start with unit tests, go to property-based testing before finally ending up in formal properties. Okay. So now, again, there's another audience interaction moment here. So I would like to hear from all of you. This question may make less sense because some of you may be like, I don't do this, so it doesn't matter. But I'll wait for a minute anyway. So here's the exercise. What are your favorite examples if you wanted to teach somebody property-based testing? Go for it. Jesper, thank you. Ooh, nice, Stephanie, that's a good one. Search trees, okay, great. Ah, nice. So some sort of like item potency kind of property, good. Okay, I'll maybe wait for one more answer. The problem is these things take a little while to type too, so it's almost, this has turned into a typing test, unfortunately. Okay, so what I'm going to do, okay, great. Torsten, Arjun. Okay, great. Good. Ah, and we've got the reverse example. Great. Okay, So thank you everybody for those answers. Let me tell you a little bit about what I found when I've had this discussion on Twitter. So Julia Evans, who's amazing. If you haven't seen her work, she's really amazingly great. And so you've got people frustrated about these sorts of things, right? It's like, look, when I look at property-based testing, they're always using like these mathy functions I don't really care about. The next quote is from David McIver, who's the creator of one of the main property-based testing tools out there called Hypothesis. And it turns out we're driving him to drink. Okay. So, of course, there are much better examples, as some of you have just given me. But what I've been looking for is, how do I make this? When you read like blog posts about PBT, they invariably have this feeling of like, it's vitamins, right? It's really good for you. Testing is good, and you can make your tests even better and stronger. Wouldn't we all want to do that, right? Whereas I've been interested in trying to find ways in which there's no choice but to do this. And so this is a curricular development that we've been working on for a little while now. So here's how we proceed, right? So we have students who are used to writing unit tests now. So now here's the conversation we have. Unit tests sometimes fail. Why does that happen? Usually the test is correct, the code is incorrect. That was the point of writing the test. Sometimes code's correct, the test is incorrect. And sometimes both are incorrect. That can happen. But the very intriguing possibility is that both are correct. The test is correct and the code is correct. So why is there a failure? Well, there's a failure because the problem statement allowed several possible outputs, and you may not have realized it. You picked one of them. The test picked one. The implementation picked another. Okay. So this is a class of problems that I like to call relational problems. If there's already a name out there in the literature, please let me know. But basically, these are things that we gave them as functions, but they're actually relations, right? And so how do we motivate this? Well, it turns out they're all over the place. So even something as simple as sorting structured data, if you have structured data, you have multiple possible orderings for the things you didn't sort on, right? There are various problems like, stable marriage problems, topological sorting, and so on and so on and so forth. Okay. And all of these problems, by the way, that I'm talking about are things that we actually cover in the first year of our curriculum, right? So even from the first year onwards, we can get students to think about this question and motivate the idea that it's not just like you want to be a better tester. You may not have a choice if you want to test these kinds of programs well. Okay? So that's the question of motivation. Now there's a question of evaluation. How do we tell whether somebody did well? Well, it's actually a very easy question, right? Because they're going to write some sort of predicate. This is valid, which is going to take an input-output pair and come back and say yes or no, right? So it's a binary classifier. We know we can do this, precision and recall. But it turns out that's not very insightful, right? Coming back with a precision and recall number, this has shades of going back to the mutation testing thing, right? You throw a large number of things at it, you come back with some answer. But what we want is something more semantic. Just like there, I was focused on the misconceptions they have. Similarly, here, I want to understand what misconceptions they have. So what we do is somewhat different. We split the property into a collection of conjuncts and check each of those separately. And the failures give us some semantic insight into what kinds of things are going wrong. Okay. So this is, again, a sequence of things we've been doing. I'll call out Sam Tobin Hochstadt here because he introduced me to Sam Susi, who's an undergrad of his, who collaborated with us on this. And so we've been trying to work on this from several different angles. In particular, we're now throwing, the second paper is kind of amusing because we actually used both hypothesis and alloy as ways of generating input-output pairs. And so there's actually a little bit of a race between humans, PBT, and SAT solvers in that paper, amongst other things, right? So there's a bunch of techniques we can bring to bear. So it's a simple question of how do we teach property-based testing as an intermediate point to getting to full-blown properties. And then we use all of these techniques that we have in this community. And so what I've shown you now is two concrete examples of, I hope, the principles that I was talking about earlier, right? So we have this general problem, and we want to get from this beginning point to this end point, and we want to do this like taking this painful path and making it a more gradual progression, where at each point students are focusing on the one new thing rather than this big overwhelming thing. right? And I gave you one example that was for very beginning students and sort of relieving the stress for very early students. The second example was basically for much more advanced students, much more into computer science, trying to go off and do more formal methods. The first example sort of depended fundamentally on things being functional. The second example drew a lot from the fact that the world is actually relational. So hopefully I'm talking to both sides of paddle here now. And Stephanie has another great example, which is John Hughes's article, which, every Hughes article is worth reading, and this one is great too. So thank you for that, Stephanie. Good. So those are two concrete examples. What I want to do now is I want to talk about where I want to go back to this question about the CS1 blob and talk about what might be a new curricular horizon. Okay. So I put up this somewhat sardonic slide. I mean, yeah, there's a little bit of like objecty stuff thrown in here as well. But fundamentally, I think the problem is we got off on the wrong footing. We've picked the wrong default data structure. And I think with a small change, we could make things a whole lot better. And I'm going to claim that the right data structure we should have been using all along, and we certainly should be using going forward, is very simply different. It's the table. Okay, the table is like the data structure nobody loves, nobody admires. It's like the Rodney Dangerfield of data structures, but it's actually immensely useful, right? First of all, it's very rich. Secondly, it's almost already completely parsed, unlike natural language where suddenly probabilities come up out of right from the beginning. And it's actually familiar even to kids. You open up a child's any secondary school student's book, and you'll find tables all over the place, not just in like math classes, but also in social studies classes. There's some very nice papers where they ask students to like take data and group them, and students will automatically draw various kinds of like group by tables. So these things are intuitively obvious to students. So it has the benefit of familiarity. Next, there's a ton of data out there that's already in this form, right? So Data Commons is one example of a website that even aggregates them. We've now done multiple studies of students at the school level in both our algebra and data science curriculum, where we've found that students are way more motivated to ask and answer computational questions if they get to work with data that are personally meaningful. Right? So you can take the same question that you were going to ask about a list of numbers, and now we're suddenly talking about a list of ages or a list of SAT scores, and it's the same question, but it's way more motivating for students. So working with real-world data sets, at least cleansed and improved data sets, has huge benefits from an educational perspective, diversity perspective, and so on. Now, there are lots of questions we can ask, right? Like, can ask a question like how many tickets are sold with a student discount. We can ask, they might be just reworded versions of questions we were going to ask before, but they become much more real when they're put in the context of a real data set. We no longer have to say, imagine that a list of numbers represents a list of ages. It can be an actual list of ages. What's better is that these are concrete questions. You can manipulate these things physically. You can print these out on piece of paper with scissors and talk about how these operations are going to perform. And also, these high-level questions lend themselves really well to questions of decomposition and planning, right? So these sort of stupid old for loop programs we've been writing have these problems underneath, but it's very hard to see. When you start thinking about them at this level, it becomes much easier to talk about these high-level questions, which is where we really want students to be headed anyway as programmers, okay? Another thing related to this is we can get past this age-old, like pointless debate about loops versus recursion, and we can start introducing students to higher-level programming operations. So again, this is Pirate code over here, and so Pirate has functions, Pirate has methods, but it also has like a language-embedded query language. And so I can write this code, and I can introduce students to these different forms of thinking about programming. I can start getting them used to query languages, so this becomes a point of departure to students who want to go off and do something like SQL, and so on, right? And we can talk about program plans because we have these very high-level operations available. Next, if you look at the particular table I've put up, right, I'm trying to take things out of this tickets column, but you'll notice that this tickets column actually has a problem in it because the data quality has some issues. So we can decide when in the curriculum we want to get to these questions of things like data quality and the consequences of bad data. In some curricula that I work with, we actually want to do this quite late. We want to start off with very high quality data so that people can focus purely on the computational aspects. If you were teaching more of a data science curriculum or you had a strong data science population, you might want to bring some of these issues in early. And so you might want less curation of your data sets. So you have this knob you can tweak Or you can even do the, one version of it in class and for homeworks, another version of it in labs, where you basically say, this was the actual data set we started with. You might want to realize that here, try the same computation and see what happens, right? So all of these things are things we have knobs we can tweak. And, let's also note that this is not a thing that you see much in the common public discourse, but data engineering is becoming a profession in itself, right? So we can motivate some of those data engineering questions that sit somewhere between computer science and data science. Next, we can start talking about, connections to the real world of data, right? So for example, I picked this sort of very canonical first name, last name structure, but some of you may know this wonderful article by Patrick McKenzie called Falsehood Programmers Believe About Names. There's actually a whole bunch of these falsehood programmers believe about names, about dates, about addresses, about locations, et cetera, et cetera. And we can start to get students motivated and excited about and intrigued by some of these questions. In fact, this article is maybe the most influential handout that I have in my course. We have a social responsible computing portion for in my introductory course, and this article blows students away. Right, for students who are, either from non sort of Western culture, either they're international students or otherwise, they immediately know this because they're like, "Ha, this speaks to me. This is me. Like I have this problem. I don't have a first name, last name. I don't have a last name." Right. But then for students who are not and who are from maybe a more Western culture, it's like, wow, I never thought about these issues. Right. So we get to start motivating some of these social conscience issues with very simple examples. And then, of course, once we start to get to real data, we can start asking questions about what's collected, what's inferred, decision making, and so on. So we can start to expose some of these perils and issues that we're dealing with in society today. We can actually build assignments, let them build these things for themselves, and see how these things can go wrong. And of course, tables are not a universal data type. So, of course, in some sense, I'm basically saying, the Prolog folks sort of had it almost right all along. Okay. And I'm seeing all this love for tables here, and hooray for tables. Spreadsheets also, of course, but the spreadsheets, tables, not exactly the same thing, but we all love tables, right? So good. Okay. But of course, tables are not universal. And in fact, there's a very nice point of departure here where you start to encode things like trees and DAGs and graphs and tables. And you say, well, actually, this kind of sucks. So yeah, we can talk about indices and so on, but maybe what we should really be doing is moving from here onto data structures. And this becomes our point of departure to introducing algebraic data types and doing sort of more conventional computer science, right? And all the stuff that CS has to offer that data science is still sort of working on. Right? So this is an approach that we call a data-centric introduction to computer science. This is a new book that we've put out. And what I want, something that I'm actually very excited about is that this is actually also a research-driven curriculum. There's a whole bunch of stuff that we're trying to study about how to do this well. It's very much work in progress, but we're looking at a very large number of different aspects of this so that we don't just have like curricula based on opinion, but actually driven by studies and understanding what's really going on. So if you're interested, there's this book. You can just read about our vision for this. There's an article in CACM, and there's a course, and all of these materials are online and free. So anybody who'd like to look at it, you're more than welcome. Reach out to me, and we'd love to chat about this. Okay. All right. So I want to wrap up my talk now and have plenty of time for Q&A. So first thing I want to point out is, look, programming is finally catching up to where we in this community have been for like 50 years now. Okay. But this, we're really good at blowing our chances, and we could do this yet again, right? So one point I want to make is, declarative programming traffics in abstraction. That's like our great power. Abstraction is powerful. It's beautiful. I love abstractions, but we should also acknowledge that they're hard. Maybe they're even unnatural. I don't know. I'm going to put that in quotes. I don't know, but it doesn't matter. I want students to get good at abstraction, but we should recognize that this isn't easy, and we shouldn't be dismissive of people who don't immediately get to it. What we should be doing is figuring out how to build techniques to get them where we want them, right? So this is my overarching research agenda. How do we enable effective learning of abstraction, right? And there's lots of different forms of this question, and this is what motivates me now, right? But the other broader point I want to make is ultimately we're going to have to take advantage of and depend on a whole bunch of other disciplines as well. We are really, really good at some things, but the title of this event is like declarative languages, right? We're really obsessed about languages, and we don't spend enough time thinking about the people who are going to be using the language. So we, for example, are really good at theories of computation, but there's all sorts of other theories out there that are not only necessary, but actually essential if we're going to want to make progress and we're going to want to succeed. right? And I feel like this has always been, not the whole community, but for many of us, this has been a blind spot, including for me, for a long period of time. It's been our blind spot, and I think we have to overcome this blind spot if we want to make progress. Okay. So I want to just recap what we did. I started off by claiming we've already won, and I think that is starting to happen in industry. Like, people are moving in the direction we'd like to see them. Maybe not as fast, maybe not using exactly the languages we'd like, but there's a lot of success over there for us to point to. Okay. But when it comes to education, there's still a very, very long ways to go. And I gave you two concrete examples at sort of opposite ends of the spectrum. One was on problem understanding. The other was about learning to write specs as illustrations of things we could be doing better. And finally, I gave you this vision about how we could be rethinking introductory computer science through this data-centric introduction. And I've given you a sense of what I think that feels like. And with that, I would like to stop speaking, and I would love to take your questions and answers. And I see there's something in the Q&A box. Let me see how far. Let me start looking at the questions. Okay, so Torsten, how far can we get in current tableless curricula if you simulate? I think that's I'm not a fan of that, Torsten. So I think there's something qualitatively different between a table as a table and all the other encodings of tables, right? Whether you think of it as a relation in Prolog or list of records or whatever, what's missing is, tables have a kind of integrity to them, right? I don't think of a row as a thing in itself. We can project out, of course, like as you notice, when I extract a column, I get a list, or I can extract out a row and I can get a struct. But I think it's important for tables to have a kind of structural integrity to them. And we've tried to do this, like in how to design programs. We have this very beautiful axiomatic construction, right? We start with, it's sort of the set theoretic, right? We start with base values, then we build up from that to small collections, and then collections of, structures, and then collections of structures, and so on. And it just doesn't feel the same at all. So maybe, the way to think about what we're doing with DCIC is it's a radical experiment, right? The radical experiment is we're writing this book. We actually start with images early on. I can tell you why later on if you're interested, but we very quickly get to tables, and we start with tables as our first real data structure, right? And maybe we can think of this as an experiment. Like, maybe you can try the experiment one way and we'll try the experiment the other way, and let's see whether we can meet up. Okay. So happy to talk more, but I think it's hard to say what's missing, because the thing is, what's missing is not a mathematical thing that's missing. I think it's a field that's missing, right? When a student comes in, they are familiar with tables. I'll give you a related thing, right? At 15 years ago, I designed a course on an introduction to computing for humanities and social science students, right? And this was specifically reaching out to an audience that is nervous about computing, right? And I wanted to get them. I had the sense of like big data was a thing that was going to happen, social media are going to be a thing. And so I wanted to get them. I was like, you're sociologists, you're going to change the way you do your discipline. But if we plunged them into programming, I think it would have been a disaster. And I think the great success there was we spent the whole first month in Excel, because most of the students coming into Brown were familiar with Excel. They didn't think of Excel as threatening. They thought of programming as threatening. And spending that month in Excel was really important stepping stone to getting to the part that was threatening, right? So I think the same way, you can say it's the same thing mathematically, but being able to touch, feel, work with a table is a thing that I think reduces the threat and increases the familiarity. That's my unverified opinion. Okay, happy to have more exchange on this. Alan says, the intro data structure is tables. Is the update API mutable or immutable? Oh yeah, well, ours is totally immutable, Alan. We're big on immutability. Mutability doesn't come up until a while later. Immutability is actually a really valuable thing to be doing here, because if you make, I mean, why am I telling you people this? But anyway, you make it mutable, you can't do experiments, right? Part of like data science is experimenting. Let me extend this with a column. Let me extend it this way. No, let me extend it that way. Ooh, that's not quite what I wanted to see. I wanted to remove this. Oh no, I want to put those rows back in. You don't want to have to think about any of that, right? And immutability works really, really well for that. So we're big fans of immutability. We don't even expose the sort of mutable table API. And I think that's totally the way to go. And you know what? It doesn't actually cause any real stress for students either. We don't have students lining up to say, like, I want to change the table and I want to change it now, right? It's like, yeah, it's fine. I got lots of versions of tables floating around, and this actually works quite well. Okay. We've actually been building a middle school programming language on top of a system called CodeApp, where we have CodeApp, but we've added function transformers to CodeApp. And it's again the same idea. Everything is functional, and you have multiple tables. We're going to start rolling that out this year, and I'm curious to see how that works out. Okay. Let's see. Harry says, I also really believe in PBT as a midpoint between unit tests. Oh, where'd that question go? And formal specs, but the mechanics can be, yeah, it is a little tricky. So that's a great question, Harry. Actually, we have two very different takes in what we do in the intro class and what we do in the formal methods course. In the formal methods course, we give them, actually in both of them, we actually start by having them write the generator themselves. And now you're pointing out that the mechanics can be tricky, and it's true. That's only if you want to write a really good generator. If you're happy with a crappy generator, it's actually a very good programming exercise to write a small generator, right? You show them a certain amount of randomness. I'm sorry, somebody said something. I thought I heard somebody say something. I'll go on, and if you need to speak up, please feel free to jump in. So writing crappy generators actually works quite well. One of the very fun things is we can actually combine the generators with our socially responsible computing curriculum. So, for example, we give them the article about falsehood programmers believe about names, and that then influences the kinds of generators that they write as well. So I think there's actually some very interesting loops there that we can tie. You're right, the mechanics can be hard, but I think it's only if you're trying to do a really good job. If you're trying to get the point across, the mechanics aren't quite so bad. And then, of course, at some point you switch to using something like hypothesis, and then this kind of becomes you actually switch to a different mechanics problem. I shouldn't say it becomes a non-issue. The generator quality becomes a non-issue. You do have different issues. But I'm happy to talk to you more, based on the experiences we have. I think it's doable. It's certainly a thing that I think from a second year college level is doable. I teach an accelerated intro class, and maybe Brown students are a little unusual, but I think it's certainly doable from a second year course onward. And love to talk more about that. Andy says, Excel has map, reduce, and lambda. And thank you, Andy and Simon, for doing that for us, your service to the community. Thank you for your service, as we like to say in the US. Could you teach the whole of that course at Start in Excel? Yeah, I'm not sure. I think, this is where things like authenticity become an issue. We didn't switch out of Excel because it's not powerful enough. We switched out because students want to feel before they leave that they've worked in a quote unquote real programming language, right? Now, I think I've gone from being a snob to thinking like anything that anyone wants to call a programming language is one, because otherwise it just becomes gatekeeping. But the reality is that students, when they're going to go out, they're going to go off and work with some data set or something. They're going to need to know how to use something like Pandas sooner or later. And I think it becomes a disservice to try to do the whole thing in Excel. So the first month in Excel is phenomenal, but then you do want to find a path out from that. Again, in our middle school curriculum, we're starting off now, as I said, in this tool called CodeApp, which is really like spreadsheets done well for middle schoolers. But then we want to transition out from that. So we go from CodeApp, then we add functions to CodeApp, not Lambda, just functions, named first order functions. And now we're looking at how to progress from that into something like Pirate, because at the end of the day, students also need to feel like they have learned a thing that they can recognize, right? And they recognize certain names and things and styles as being programming. Look, I think more harm has been done by movies than we can possibly imagine, because everybody knows from movies that a program must be text. It must be typed, it must be on a screen, and sometimes it's green and it scrolls quickly, right? And people form really strong impressions from this. And those impressions, if we don't combat, they end up feeling like, I didn't really get what I came for. Okay, so that's maybe not exactly the answer that we would like to give, but I think that we do have to take some of those issues into account. Next, hi Ohad. Do types ever get in the way? What are the pain points? That's a really good question. I actually would like to make a pitch. We've just put out a thing called a benchmark for tabular types. Look for B2T2, the Brown benchmark for tabular types. What we're trying to do is we're trying to get people to tell us how well they can type tables. What we did was actually start with uh, the way tables are programmed in a bunch of untyped languages or dynamic languages. So we looked at Python and Julia and R. Because we wanted to see what happens if people are not constrained by types. And then from that, we've distilled a benchmark of functions that's actually useful even if you're just designing a dynamically typed table processing language. We've distilled functions. We've distilled some sort of typing challenges. We've also got a collection of erroneous programs because we would like people who build type systems to also tell us what the ergonomics are. This is the thing that's often overlooked. And so there are erroneous programs, and you can report the quality of error reporting that you have. We also want to make it possible that somebody might say, look, I have a type system that works really well, but the errors are crappy. And the new contribution is I've simply improved the quality of errors. And right now that's kind of hard to do. And the benchmark enables you to do that as well. Okay, so that's a long detour answer to get to the question of and I would like people to go look at this. I think there's some fun stuff there, and we're actually asking people to make contributions. So, and we've started to have some people who have typed languages for tables making contributions, showing us how they implement the different parts of the benchmark. There's also a data sheet, so you can report exactly what you did, so we can easily compare. I want to improve the quality of science here, basically. So, how much do types get in the way? This is a tricky question. Many of the problems we have observed from our beginning students are not so type level, but it's also a little complicated to answer because Pirate is it's a sort of roughly speaking a gradually typed language. So Pirate has annotations. You can put type annotations in. They check dynamically. Their checking doesn't mean exactly what some people might think it means, but it turns out it's actually students don't notice that things aren't statically checked. There's a very interesting question of whether students even understand what static type checking is, right? They put annotations, they get some errors, and I have students who've programmed in Java extensively before, and they don't realize that the annotations they wrote are actually being checked dynamically. Right. So I think there's actually a very complicated question here about understanding what people really mean, what students get from types, and what we mean and what they understand are very, very different things. Having some degree of annotation has been very, very useful. Having too much annotation may or may not make that much difference. In Pirate, you can actually turn the type checker on and off. You can run it in typed mode or you can run it without type checking. The tables are tricky because we don't have good types for tables. This is actually what launched. We did a grad seminar to try to understand what the world of tabular types looked like. We found there was so much incomparability in there that we went off and built a benchmark. So we've gone in this long detour. We don't have good types. So I think types get in the way. Do types get in the way? Right now, not really, but we don't use them quite as much as one might wish. But I'm just going to say that we really don't know. I think types in particular is a place where we have a lot of heat and very little light. There's a few studies. Andreas Steffik and Stefan Hannenberg most famously have done a few studies. I think those studies are only partially representative because a set of tasks. I mean, the problem with these kinds of studies is always like, what tasks did you do? What languages did you use? And so on. And many of these are not in type systems that we would particularly care for or appreciate in this community. So I think it's a wide open question, and we need to study a lot more about this to really understand what's going on. So short answer is we don't really know. That's not a very satisfying answer, but I think that's the most scientifically honest answer I can give. Um, James has a question. Do you find the good IDE support important for beginners? That's a really good question. And I think this is another place where, as you're noting, James, I mean, there's a question about what works well for beginners versus what works well for more advanced programmers may not be the same. We have purposely chosen to not build any auto completion support in the Pirate IDE, partly to see how much of that is actually a problem. And I think the jury to me is very much out on this. I don't really know. We don't find it necessary, but then, of course, we are not the right people to decide this. I don't yet know of any good studies on this, and I think this is a very ripe question to study. Part of my concern is uh, how do we say this? What are we studying, right? And who are we studying it with? Because these days we get students, we like to think of students, for example, an intro college student as kind of this tabula rasa, right? Like we're going to teach them computer science, we're going to teach them programming or something like that. Um, but that's actually complete nonsense, right? More and more and more students are coming with a huge amount of like computer science in high school, or at least a little bit of computer science. Most of them have now programmed in a language like Scratch. So what does an IDE even mean to a person like that? Like what they might really want is not any of these things. They might want Scratch. But then, of course, we also know that people really load Scratch because they feel it's not like real programming because it's blocks. And we know that's not programming. Programming is done in text. So there's actually a very complicated set of issues going on in students' heads that we have to unpack these issues before we can get to good answers here. Um, I don't know. That's not really an answer to your question, I know, but I'm not sure there is a good answer either, unfortunately. So hopefully that helps a little bit, James. But feel free to ask a follow up if that doesn't. Let me see. There were some comments in chat. Let me just see what's going on over there. Uh, okay, Andy. Yes, sorry. That's the Excel question, I presume. And yes, okay. And the benchmark. Yeah, good. Yeah, cool. Thank you. All right. We're starting to run out of time, but if there's any last questions, I'm happy to take them. If not, give everybody a break. I know it's been a bit of a fire hose here. Do you deal with a lot of tension between conflicting incentives between research and education? Oh, hey, that's a great question. Um, no, and partly, I guess maybe I've had this issue. I've been a bit of not good at being mainstream for a long time. I mean, I started doing computing education back when I was in grad school, when it was a really, really bad idea. And by the way, so did Stephanie. Stephanie and I collaborated back then. I don't want, sorry, Stephanie, I don't mean to embarrass you in public like this, but we've known each other for a long time and we worked together back then. And so even as a grad student, back when I was a grad student, it was understood that you don't do education. That's for like old retired people. And I decided it was more important to do what I found interesting. So I've always like what I've done successfully is basically keep alive a actual publication record that makes me pass for somebody who's kind of who looks normal, and do this kind of on the side. But now I'm sort of I'm too old to give no F's left to give, so I can feel free to do whatever I want. What I would say to students is, hey, look, if you feel like education is an important question, the great thing is it is actually a really hard problem, right? To my mind, it is actually the hardest thing that I work on because I have a whole bunch of technical issues I want to solve. I'm messing around with SAT solvers and PBT and this and that, right? All the technical stuff that I do. But there are also humans in the mix, and humans are terrible. We can't control them. They sort of do their own thing, and they've got like all kinds of complicated things going on in their heads. And so it's actually really fun and hard to work on the combination of technical stuff and humans, right? And so yeah, exactly. So I want to make a case, like we're starting to get a community going on user studies and so on for programming languages. There's a lot of good people. Last summer, by the way, we put together what we call a swimmer school. That was sort of a summer plus winter school. We wanted to be, say, hemispheric neutral. We put together a swimmer school on PL plus HCI. It's all archived. You can find this on GitHub. I don't know. Somebody can probably. I can't get the URL right now. Maybe somebody can post the URL into chat. So all of that's archived. We might do one again in the future, or maybe somebody else will do one. So there's this growing community. So there's always a lightweight way to do this, which is just to do like HCI plus PL. But then there's a heavyweight way to do it, which is go all the way to education. And you can do this also in stages. And if you do it, the good thing is I think people are starting to recognize this now. Partly, as Antonio said at the beginning, I made a very conscious public decision to move into education about 5-6 years ago, partly because we don't have people willing to do that, right? We still have the sort of stigma of like education is like the silly thing that like old retired people do. And I wanted to be like, I don't think I'm old and retired yet, but I wanted to consciously put myself out there and say like, I'm willing to do it. Who wants to join me? So I think as more of us do it, there's less stigma associated with it. And when there's no stigma, there's no tension anymore. Now, one fun thing is in the design of Pirate, which is this language I've mentioned multiple times, we made a really conscious decision, and this was the hard one, to not do any research, right? Because the moment you make this a research project, you start working on innovation and you focus on that thing and you ignore all the other aspects. That's kind of the way it has to be, right? Our goal was to make a language that has a really, really awesome experience for students and not worry about whether we get a single paper out of it. We have accidentally produced one or two papers along the way, sorry. But by and large, it's not a paper generating mill. It's just like to create a really awesome experience. But what it does enable is our ability to do all this other research, and we do that, right? So one thing we don't do is we do not surveil students. We're very anti-surveillance, even though it disables some research we'd like to do, but we want to protect student privacy. We take that very, very seriously. So there's some research we can't do, but it still enables us to do a whole bunch of other research, and education research. So I would say that there's a whole spectrum now available that was not available when I was a grad student, and you can position yourself anywhere you want on that spectrum, and you can do it sort of unashamedly now, if that helps. Any other questions?
I think
Antonio, I'm sorry, I've taken too much time. Thank you so much. Thank
no,
you. Thank you.
Shriram, I mean, you were so good that I didn't actually have to work as a moderator. I mean, very, very brilliant. I liked very much your talk, and you were also very quick and effective in doing the question answering. So I think a big clap for you. Remotely,
Thank you so
we
much.
don't have this clap. So thanks again for this very inspiring talk, and thanks also for all the people who participated and for the
Yes.
many questions.
Yes. Thank you.
So
Thank you.
thank
Thank
you.
you.
We should now have